Good evening, Doctor. This is Nachamba de Mariam from SWML 53, and I'm going to present the Lendshield AI, and this is a dual module ensemble architecture for microfinance and circles. Basically, I'm going to go straight into the presentation, and these are the contents of our presentation. I have the introduction, the related work, problem statement, research questions and objectives, the research contributions, methodology, architecture, the dataset description, the results, limitations, conclusions, and future works, references, and acknowledgement. To dive direct into the background and introduction, Uganda's microfinance sector has over 20,000 Uganda SACCOs, and it's managing 3 trillion Ugandan shillings annually outside formal credit bureaus. And we analyzed a portfolio at risk of 15 to 25% in Uganda versus the one in the world, or you could call it the global benchmark, which is only 5%. And that means that up to 25 Ugandan shillings per 100 lent may never return. And what does that do? That's, of course, it brings losses to the economy. And then we looked at some of the causes. We looked at the credit bureau gap. Since it's a tier 4 institutions, they cannot check cross-institution borrowing, and there is a silent double dipping, which is undetectable. We looked at one of the basic reasons for this. It's because of the appraisal bias. Appraisal bias basically favors people to acquire loans who are not worthy, but acquire them because of relationships they have with them. And a dual model works with 2 modules, one which is the gatekeeper, and this gatekeeper acts like a pre-disbursement, and this pre-disbursement is like it's like a controller to know if someone is worthy to acquire a loan, and to see if the person is worthy to get credit. And there is the second model, which is the monitor, but it's a post-disbursement. This monitors the loan after it has been acquired, and it has 3 class early warnings: the stable, elevated, and the critical for the active loans. We had the XG Boost. XG Boost is a module that we used, and it showed that there is an optimal inductive bias for heterogeneous tabular credit data with missing names, and it boosted the gradient trees. Then we used the Sharp, and this was based on the model agnostic attribution, which is satisfying Uganda Data Protection Act of 2019. This is the area under precision curve, and it has a ratio of 4.2 to 1 class imbalance. Then there is a group shuffle split, and it split the train tests, and it evaluated entirely unseen cooperatives. This is the related work. We had AI in banking. It's basically based on regression analysis for credit risk. It used the logistic regression because it is a linear model, and then the results were area under curve was 0.71 to 0.78, and the limitation was that it requires formal credit history, and it is not applicable to Uganda, which is a tier 4. Then we also had the effective credit risk prediction, which uses ensemble classifiers, and it used the random forests. And the limitation was single institution data set and the limited geographic generalizability. This is basically related work. I'll dive straight into the problem statement. The problem statement, the first three problem statements that we saw is the appraisal bias. Appraisal bias is when the loan officers approve based on relationships, not because of the repayment capacity. Like someone can acquire a loan, can come to acquire for a 10 million loan, but in actual sense, they can pay 2 millions. But because you know this person or you have a relationship with them, you just give them a loan, and those are some of the reasons for the loan defaults. Then we also have the identity and trust gap. In Uganda, a few people, actually, some people do acquire loans without their credentials. Like they can use other people's identity card, they can use other people's collateral to acquire the loan. So that leads to identity and trust, to low identity and trust between the borrower and the lender. Then there is the blind spot. The blind spot is where there are no early warnings for deteriorating loans, and by the time a loan is formally non-performing, collateral may be gone and recovery near impossible. So we had the computational problem. This was a 3.1 to 1 ratio of class imbalance. And this showed that there is 24.53% default rate, and the rest being the non-default rate. And this classifier achieved 75% accuracy while detecting zero defaults, and this is a complete metric illusion. So we dived into the research questions. Of course, I want to get straight into the gist of the presentation. The research questions were: one, we had to conduct a 24-question EDA on 19,955 training eligible SACCO loan records, and we filtered these ones from the 20,846 raw records to identify the data quality dimensions and high signal predictive features for the first model. And the research question we had about it was what borrower loan structure and contextual feature carry the highest predictive signal for loan default in Uganda's SACCO sector. Then the second question was to design, train, and compare 5 machine learning architectures, the logistic regression, random forest, XGBoost, TabNet, Tab Transformer. And we asked ourselves which machine learning architecture among all these 5 achieves the best recall-weighted performance under the SACCO disjoint evaluation. The third question, the third objective, we had to deploy a Flask REST API, and this was embedding the validated XGBoost pipeline with sharp-based advanced action explanations for pre-disbursement credit scoring. And the question was, what early repayment trajectory features reliably distinguish the stable, elevated, and critical risk states in active SACCO portfolios? This basically deals with the second module, the one for the monitoring. And then the fourth question was to establish, the fourth objective, was to establish a 3-phase deployment framework. And it was from the shadow to assisted to the policy with measurable SACCO level performance. And the question we had was, how can sharp-based explanations be structured to provide actionable, regulation-compliant, advanced action reason for Uganda loan officers? The research contributions, we conducted a 24-question EDA framework. This is in our slides, and then it's also in our IEE. Then we performed a 5-model comparative evaluation under leakage hardened protocol. And this involves the basic five we use: the logistic regression, XGBoost, TabNet, and transformer, including the 7-step leakage audit, confirming a 0 cross split. And it involves basically the borrower loan count, the loan duration, and is repeat borrower. Those are variables we use basically for this. Then we deployed a production-ready XGBoost scoring API with sharp explainability, as I will show you in deployment. Then we establish a trusted MVP with a 3-phase deployment framework. We have two modules we are working with. We have the application gatekeeper. This works on pre-disbursement of the loan. And then we have the second module which works on the post-disbursement of the loan. These are the input variables we use: the borrower demographics, the loan request, collateral verification flags. There were 83 features. And then for the input, we have the repayment data, arrears, current balance, then days since maturity. I'll go straight into the module architecture and mathematical foundations. Here we have the XGBoost. We are going to first look at the XGBoost since it's the basic model that gave us constructive results. So the XGBoost uses decision trees sequentially, and each correcting the residual errors from the previous assemble. This objective function balances prediction quality and model complexity. So each boosting round fits a new tree to the first and second order gradient statistics of the log loss. As you can see here, when tree 1 occurs, it predicts the residuals from base. Then when the second tree, this one is the refiner, it targets errors from the first tree. What I say that it corrects residual errors from the previous assemble. Then the third is the polisher, and this one fixes the 2% mistakes from the second tree. Sorry, it fixes the mistakes from the second tree. And then the last tree, it shows the 600 tiny corrections in total. This also uses a sigmoid function. While with the total study, it includes 19,955 records. So I'll proceed to our models as at large. So we had the logistic model. The logistic model is a linear combination of input features mapped through the sigmoid function. This is the function. So the problem is that when it's training, it minimizes the binary cross entropy via the gradient descent, and it didn't work out well for us because it basically looks at the linear features only. And then we went to the random forest. The random forest trains n independent decision trees on samples, and it averages their probability outputs, as you can see here. Then we went to the CatBoost. The CatBoost, it just orders boosting for circle heterogeneity as, okay, it's, the CatBoost doesn't, okay, for us, it just orders, let me say that, it does ordering. And then we have the light GBM. The light GBM is like a leaf-wise growth for edge device efficiency. How I can explain this is that okay, it's like when the light GBM adopts a leaf-wise or the best first growth strategy, it focuses on the computational effort on the leaf with the highest loss reduction, and then it enables deeper and more accurate trees with lower memory usage. So here, as you can see, the function, it leverages the gradient base on side sampling to retain all high gradient loan applications while randomly sampling low gradient instances. Then we had the EBM. This is the glass box for regulatory compliance. This is the mathematical function. Then we have the tabnet. Sorry. Then we have the tabnet. The tabnet is a sequential sparse attention, and it applies a sparse mask method, as you can see. Then we have the tab transformer, which maps categories to dense embeddings. I'll go straight to the next. These are the data set descriptions and explanatory data analysis. In our data description, we had 19,955 training records from 46 circles across 15 districts, and it filtered from the 20,846 raw records. This is the graph for the Clancy balance, and this one deals with the default monotonic relationship. This is for the borrower loyalty effect, and this is for the school fee seasonal effect. This happens in seasons when students are going back to school. Then this is borrower loyalty effect. The number of times the borrower acquires loans from the circles. Then the class imbalance. We look at the balance between first-time applicants and the monotonous applicants. I'll continue to the next. These are the output results from the discussion. Then we have the cross cooperative stability analysis, and this looks at the splits that we had among the models. Then we have the explainable AI results and discussion. So here we looked at how these models were varying with different features. And this one was for the impact on default probability. This was for why there are high-risk loans rejected. Then this was for why there are low-risk loans accepted. Basically, we had to perform a model selection and deployment. Models selected for deployment. We selected the XGBoost, which is the production model. The XGBoost, why we chose this XGBoost is that it had a base cross circle stability, and it confirmed clean causal features, which led to the 7-step leakage audit, and it had a threshold of 0.117. And then we deployed in a scalar pipeline, the imputer robust scalar. And this is the deployment plan that we had. The deployment plan had phase 1, which is the shadow mode, which runs parallel with manual process, predictions logged. And phase 2 was the assisted decisioning, where high-risk applicants routed to senior officers with sharp list. And then phase 3 was the policy integration, where we automated decisions from F2, which is greater or equal to 0.70, and it sustains 60 days. And if it's brighter, it is less than 0.1. We carried out a model compression on knowledge distillation. Here, the rationale for choosing knowledge distillation, we had preservation for complex nonlinear logistic, and then the architectural simplicity and dark knowledge transfer. So from the mathematical framework, we had the extract, the transform, and the distill. So in the extract, it reveals the hidden relationships between classes by smoothing the teacher's confidence. And then in the transform, it strips the sigmoid compression to retrieve the teacher's raw decision conviction. And then in the distill, it creates the expert advice. and targets the student model is trained to mimic. This is the distillation pipeline. So in the distillation pipeline, we had the data loading and identity preprocessing. Then we went to that establishing the teacher's baseline. And then we had the generating soft labels. Then we went to the loss blending, and this is the function we came up with. And eventually the student training evaluation and selection. This is the full comparison of the teacher versus the student baseline and versus the distilled students. The threshold, the accuracy, precision, as you can see. And then the performance breakthrough here, the student surpasses the teacher. Why? There is a single decision tree student that achieved significant performance gains over the 600 tree XG boost teacher baseline. So the key metrics and performance uplift was that F2, which is the primary metric, was on 0.7412, and it's versing the teacher who was on 0.6, which is at 121.4%. This makes a justification that knowledge distillation as regularization and the label smoothing effect was T equal to 2. So this is the URL for the API that we rendered. I'll click on it so that we see how it works. I'll go to my I'll go to my browser to check with it. But basically, this is the interface for the API. And then it shows the borrower details. You enter your details, then you score the application, and you see the risk of either defaulting or the percentage at which someone may not default. The limitation we faced was the data quality. In Uganda, we have a problem of inconsistency in data, and also we have a lot of manual data more than the digitized data. So that was one of the limitations. Then on the second module, we had an evaluation scope. Basically here it deferred to a companion publication, and the results presented here only cover for module 1. So module 2 becomes weaker to be used. Then we had a geographical institutional focus, and this was it brought up minority class sparsity, which remains a challenge, and it potentially leads to conservative scoring in volatile edge cases. Then we also have the class balance, which has a ratio of 3.1 to 1. And this also brings a minority class sparsity, which remains a challenge. And these are some of the solutions we can use. And in conclusion, Lendshield AI is the first circle disjoint leakage audited machine learning credit framework for Uganda's Tier 4 microfinance sector, addressing a critical gap in East African fintech. The feature works we have is we want to carry out a phase 2 data collection, and we target null fields like linked savings, days to disperse via the direct ETL integration with Circle core banking systems. We also look at doing a formal fairness audit, a federated learning, USSD mobile interface, where we can score interface for loan officers in areas with limited internet connectivity. Then you also have the deep modern stability. And this will help us to carry a full tabnet plus tab transformer stability analysis on expanded phase 2 dataset. These are the references we used. We acknowledge the supervisor, our beloved Dr. Galiwangu Marvin, and Madam Dr. Reference Eunice Namujeni. We honor you so much. Makerere University, College of Computing and Information Sciences, our circle partners who trust us with a data set, over 60 plus Ugandan circles, and then the community, the Uganda Microfinance Regulatory Authority, Bank of Uganda, and East African FinTech Community, whose regulatory frameworks and standards guided the compliance architecture. I remain Nashamba de Mariam. Have a blessed evening.